Hi, this is Dr. S.P. Asaf from Mechanical and Industrial Department, IIT Roorkee. In the course of vibration control, we are in the module 3 in which we discussed about the main vibration generation mechanism and the vibration isolation features. So now this is the last lecture of this module 3 in which you see here. Now we are going to discuss about the numerical problems of the vibration generation mechanism and the isolators. We discussed about in the vibration isolation that what exactly the insertion losses are there, how we can calculate those when they are being dissipated through even the airborne or the structure borne things. And also we discussed about the various features of the foundation part, in which when we have a rigid foundation or the flexible foundation and then we are putting the isolator together, then how the vibration can be suppressed, or we can simply reduce the vibration amplitude. In the previous class, we were discussing about one form of the vibration generation mechanism in which we discussed about the damping models and the measures of the damping, and we found that here there are lots of factors is directly affecting the material damping. So when we are talking about a material damping with the constant figure that this is the material and material is there and this is what the microstructure of the material, we can take a constant value, is not true. And even when we are going with the different types of material, then we know that even when the transformation of the kinetic energy or the strain energy in the dissipation form here, and which is being transferred into the heat, always the grain structure, the grain size and even the grain boundaries are directly affected by this kind of formation of heat. So when we were discussing about the viscoelastic material, we could even find out that because of the viscosity and with the elastic feature of that material, there is the hysteresis loop was there, which was simply showing the loss of energy. And this loss of energy is creating more problem in the formulation of the total amplitude of the viscosity, which is being provided by these kind of materials. Even we discussed some of the numerical aspect of this, that how the damping coefficients can be calculated in a complex form when you have nth degree of freedom system, and how the matrix multiplications are being there just to justify the symmetric nature of our damping part. And in that also we discussed about the damping ratio for the underdamped or for critically damped system. So this part here which we discussed in the previous class. So today now we are going to discuss about the numerical problems in this chapter, in which we discussed about the vibration generation and the isolator feature. So the first numerical is, we have in the industrial facility there is a machine with the gear, and due to the meshing fault it generates the large amount of vibration at the frequency of 550 hertz. So the frequency is given to us, which is propagated to the 18 millimeter thick ceiling of the local beneath in that. So that means here at the below of this machine we have a 18 millimeter thickness, the ceiling was there, and in that ceiling the dimension is L into B, that means the length into breadth is 12 into 8 meters square. And the average RMS velocity is also being given in the meter per second, which can be easily measured, and the the velocity amplitude to the walls and the floors are negligible. So here we are not going to consider the velocity component which are being there with the walls or the floors towards the transmission feature. So we are very much focused to this local part, and the sound level with this is also being we can say the partly generated as the transmission of the vibrations are there, and we can say that it is almost near about the 84 decibel unit in this. So we can say that the equivalent absorption area of the local, because we are just going with the local part, is almost, you see here, the alpha E, which is like we can say a relatively hard acoustically feature because of the material property, the alpha E is less than 0.3, can be estimated at around we can say 24 meters square per second in 500 hertz of the octave band. And below that we have the concrete floor, which has the elastic modulus of 2 into 10 to the power 10 and the density is 2.3 into 10 to the power 3 kilogram per meters cube, and you see the Poisson ratio for such kind of things can be straightway taken as 0.3. And you see here the air which is being circulated there, we can take the specific impedance as 400 Newton second per meter cube. So, these are the input parameters which are directly interacted with the machine, and you see like when the sound, when this vibration is propagated along with like we have the ceiling which of 18 millimeter thick, and then you see all these dimensions are there. Now, the first thing we would like to find out the coincidence frequency of the ceiling because of the machine excitation. Second, the power, the sound power which is being radiated due to the meshing fault, because we have now the exciting frequency, then how much power is being radiated through this ceiling. And you see here, because and it is due to mainly the meshing fault, and how much like the sound level can be created or it can be reduced if the ceiling vibration can be completely eliminated. So, when we are trying to now reduce the vibration or eliminate the vibration, will it be there any sound there itself or not? So, you see these are the three different aspects of the sound and vibration interaction when you are in the industry, and it is a very common problem, practical problem is there, which was taken by the handbook of you see like the sound and vibration of the KTH Sweden. So, now we need to make a strategy to solve this problem. So, first of all we need to find out the radiation frequency of the vibrating ceiling, so that we can at least you see find out that how much transformation is there with the specified size of the ceiling. Then we need to go with the radiated sound which is being transmitted through that, and then we need to find out the sound level when you see we know that the like there is a clear radiation and the vibration excitation is being just passing through these ceiling towards the ground of the concrete. So, the first to see here, in the first case we need to see the ceiling can be regarded as a large plate as we can see, and the coincidence frequency of these joists in the like the chapter number 15th we discussed can be find out by Fc equals to Kc divided by H, where H is the plate thickness which we have already considered as the 18 millimeter. And when we are putting these things, and we know that you see here like this Kh value is also given in this way. So, you have the plate thickness 0.18, you have the Kc which is nothing but the constant value for like this concrete feature. So, we can get the F which is nothing but you see the exciting frequency of this, we can say the ceiling Fc is nothing but equals to 18 divided by 0.18 which is nothing but equals to 100 hertz. So, this is my coincidence frequency like of the joist with the ceiling, and we can get that part. So, the ceiling vibration according to this excitation can occur at the frequency of 550 hertz, well above the coincidence frequency. So, that means you see the radiation energy can be easily approximated as the unit value, because the excitation frequency which is the ceiling excitation frequency is the 100 hertz, which is like the we can say the natural frequency of that, and the exciting frequency due to that is 550 hertz is you see the huge values, the huge differences are there. So, it can be well up like taken as you see like the radiation efficiency is almost near about the 1, and then we can straightway calculate that how much like the sound power in terms of the acoustical radiation, as we discussed already in the like the lecture 15, is S, which is the efficiency, into the rho 0, that is my density, into C, V square here. So we know that the S is 1, as we know that there is a clear difference and well above the coincidence part of that. Second, the rho 0 which was given as the 2.2 into 10 raised to power this, and the 400 is given as you see like the other part. So when we are formulating each, we have the sound power as 1.86 into 10 raised to power minus 3 watt. So this much you see like the sound power is being transmitted and generated along the machine itself by transmission of this much vibration at the 550 Hertz exciting frequency. And the Selling's contribution to the sound pressure level in this river bend field can be easily calculated with the sound level at that point is nothing but equals to LW plus 10 logarithmic of 4 divided by A. So when we are putting these values there, the sound power level is LP is nothing but equals to like the 10 into log of 1.86 into 10 raised to power minus 3, which was you see the sound generated, divided by 10 raised to power minus 12, plus that was you see the LW plus 10 log 4 by A, that was the 24. So it is nothing but equals to 84.9 dB. And the contribution to the total sound level can be straightway find out when you are just using the weighting factor, and here the weighting factor in that, which was discussed in one of the table there, the A weighting factor for 500 Hertz sound in any octave band, we can say that the LA, the sound band you see at the ceiling is nothing but equals to the 84.9 dB, which was calculated earlier, minus 3.2, that is 81.7. So the reduction of the total sound level, if like it is contributed from the ceiling, can be completely eliminated, and based on that you see that we can simply find that the delta L, which is like LA, which we just want to like eliminate that point, is 84 minus 10 log 10 raised to power 84 by 10 minus 10 to the power 81.7 by 10, or else we can say that it is 84 minus 80.1, almost near about the 4 dB. So means that you see here, when we are just trying to eliminate the entire vibration from this, which is being excited above 500 Hertz, we can say 81.7. When we are trying to do these things, the sound which is being there at the time is 4 decibel sound. So that means you see here that much energy, the sound level, the sound power or the energy is being available when even like the contribution of the ceiling is like absolutely eliminated. So that means you see here that much amount of energy is being there due to various other sources. So in this numerical you see here, we could easily figure out and interact the radiation, acoustical radiation in form of sound generation, and the same time you see here how the vibration is really being contributed, and if you want to eliminate those things, how we can compute or how we can interact those features together. Now when we are moving to the another question, then we have you see a chimney, which we discussed that you see here straight chimneys are there in many of the industries. A straight 30-meter high circular cylindrical chimney stack is erected on the ground of any of the industrial part. So we have the height is 30 meter only. The material of is this one is the steel, for which you see the material property can be immediately put the elastic modulus 2 into 10 to the power 11 Newton per meter square, and also the density is 7.8 into 10 to the power 3 kilogram per meter cube. The outer diameter D0 is also given as 1 meter, and the thickness is also 1 centimeter, and the chimney can be moreover we can say rigidly fixed to the ground, certainly like because of the proper excitations and the rested ground part. Now we would like to find out the lowest wind speed at which the resonant bending vibration of the chimney stacks are excited due to the vertex shading. This is what one of the basic cause in that how the vertex shadings are basically being there to excite the entire chimney under the bending vibrations. First of all, in this we know that we need to apply the Euler-Bernoulli beam excitation theory, as like the 30-meter entire chimney is being there, which is at one end it's rigidly fixed. So now you see here the lowest eigenfrequencies for this through these Arnold-Bernoulli like beam theory table is K1 into L as equals to 1.875, and since the L here is 30 meter, so we can say that the bending wave number for this is the Kb square equals to W into square root of rho s by EIB. So we could easily find out that how much wave numbers are there for this 30 meter L. So when we are solving this for eigenfrequency, the eigenfrequency is nothing but equals to K1 L square divided by 2 pi L square into 1 over this the part which we discussed, square root of rho s by EIB. EIB is nothing but equals to the modulus of rigidity for the beam, and we can put entire things together. You see here that 1.875 as KL, which we calculated for the beam from the table, divided by 2 pi L square is 2 pi into L is 30, so 30 squared into 1 over the rho s. The rho is the density of that material and it's a steel one, so it is 7800. The S is nothing but equals to the total area, we can say pi by 4, 1 square minus 0.98 square divided by, that is what the effective feature is, divided by the EI, Young's modulus is already given in 2 into 10 to the power 11, and I is the moment of inertia, so it is pi by 64, 1 to the power 4 means because it is like the cylindrical chimney which has inner and outer diameter, so 1 was the outer diameter, 1 to the power 4 minus 0.98 to the power 4. When we are formulating this, it is almost nearly equal to 1.10 or 1.108, so it is 1.1 hertz. So when the wind blows past the chimney, the vortices are absolutely generated, and when they are subsequently released, then the stack is absolutely excited, and the characteristic shedding frequency at which it is excited is 1.1 hertz, and that frequency which even we can calculate for this, it is equal to 0.2 u by d. U is nothing but you see the velocity, and d is the path or which it is being passed, the entire air is being passed through. So we can say it is the speed where you see u, the flow or the wind velocity is coming, and outer diameter of d is given to us. So we can solve for this wind speed, and we can evaluate by entering these parameters. So it is nothing but equals to, we can say that Vu which we would like to see, d divided by 0.2 into f, the f was calculated already, the excited frequency 1.1 hertz, the outer diameter was given as 1 meter. So we can say that the u, this is what the velocity or we can say the blow or the flow or wind velocity, whatever you can say, of the air when this much exciting frequencies can be generated, that is 5.5 meter per second. So we can say that you see this shedding frequency of 1.1 hertz can be straightway we can say find out when you have a very specific flow velocity together. And this wind blows are the clear cause of this exciting frequency when these winds are being released throughout the chimney and it is being excited there. So this was the problem in which you see here there is a clear excitation of the chimney when the air flow is there, and that part which we discussed in the flow induced vibration in which the air was flowing or the fluid is flowing through the chimney or the pipe or any kind of the closed conduit. Now in the third problem, a 2 kilogram machine is being elastically mounted to the set of concrete joists or the beam foundation, which is a very common device you see in any of the industry. The isolator, which may be regarded as the massless spring, has the spring rate as 10 to the power 7 Newton per meter. That is what my stiffness of the springs are, the material property. The thickness of the beam foundation where the machine is being installed is 20 centimeter. Now the machine is generating the vibration in the band of 100 to 200 hertz only. Now you see here we would like to see that you see here how we can model these things, whether it is perfectly okay or not, and we just want to see that how we can take the necessary step to account the flexibility of this being foundation by calculating what the insertion loss is of the vibration isolator when the foundation is regarded as rigid first. Second, the same you see here when the foundation is regarded as the very large concrete plate, and the relevant material property of the concrete is the density, as we have already taken 2300 kilogram per meter cube. The Young's modulus as it is given you see here, the 2 into 10 to the power 11 Newton per meter square, and the Poisson ratio is 0.25. Assume that now in the third case that the error of 5 decibel can be tolerated. So, with this assumptions, is the simpler model can be acceptable for the entire frequency range of 100 to 200 hertz, or do we need to change in the model to formulate this thing? So, as we know that the insertion losses of the vibration isolator can be straightway calculate when the foundation is solid is nothing but equals to 20 log 1 minus omega square divided by k by m, where we can calculate the omega as the exciting frequencies, like you see when we know that 2 pi f square, and the stiffness is given to us, the mass is given to us. So, for 200 hertz say, now we are going towards the higher mode of this excitation, we can say the insertion loss for 200 hertz is 20 log 1 minus, since it is you see 200, so 2 pi 200 square divided by the k is given as 10 to the power 7 divided by the m is given as 200. So, it is almost you see the insertion losses are 30 decibels. Now, we know that you see we need to act in such a way that what exactly the transmissions are. So, y of m is nothing but equals to 1 divided by I omega m, and y of L, when y of like the I through that the transmission part, it is nothing but equals to I omega divided by k. So, when we are talking about the machine feature, it is nothing but we can straightway calculate that what exactly the exciting frequencies are related to the mass. So, that is why you see it is 1 by I omega m, and when we are talking about the restoring features, then it is I omega by k. So, y of p of this, that means you see here the particular feature of this y of p is nothing but equals to the square root of 3 1 minus Poisson ratio square divided by 4n square root of rho into E. So, we can straightaway calculate this by keeping the 0.25 as the Poisson ratio. We know the h 0.2 which was given earlier, and rho is 2300 and E is given as 2.6 into 10 to the power 10 as the elastic property of this. So, Yp is nothing but equals to 1.36 into 10 to the power 6 minus 6 meter part was there. So, when we are now just adopting this insertion loss at the 200 hertz, so now we can put these entire features in, means you see here the Ym, Yi and Yp together you see here, when we are keeping these things, now our the insertion loss at 200 hertz is nothing but equals to 20 into log of 1 divided by 2 pi, since it is at 200. So, like omega square, so it is 200 into 200 f square plus I iota times 2 pi f divided by 10 to the power 7. That means you see here we have a clear stiffness variation. So, 2 means iota times 2 pi, as we know that you see here which we discussed, iota 2 pi omega divided by k. So, that is you see the yi and ym is 1 by iota 2 pi into m. So, we have this one. So, this is what it is, plus the Yp, that is 1.36 into 10 to the power minus 6 divided by the entire feature, means we have all three yi plus ym plus yp divided by ym plus yp. So, it is 1 by iota 2 pi 200 and 200 plus 1.36 into 10 to the power 6 minus 6 as yp. When we are evaluating this in formation of you see like iota terms and like making equation of the features, with this all numerical manipulations, we can say it is equals to 20 into log 122 divided by 4.21, or else it is nearly equals to 29 decibel. So that means, you see here now, we know that the insertion loss of the vibration isolator at the 200 200 hertz frequency, when we are computing all, means the DL at 200 is, when we are computing DL at 200 hertz is YM, YI and YP, they are giving clear feature of the 29 decibel. So even when you are computing with the individual part of this, or when we are comparing these things, they are clearly giving a well featured that you see how much insertion losses are there when you just combine together. So this was, you see, the second part was there, you see, when the foundation is just a large concrete plate and everything was there. So 29 decibel was there, and when you simply taken the rigid foundation, then the 30 decibel was there. And now you see here, when we are saying that this is what the model through which we can simply control the entire part, or is it acceptable feature, we can say the simpler model can give, you see, an accurate, not exactly so, but almost accurate solution to the entire frequency interval of 100 to 200 hertz. And but you see, when there is an increasing effect of the beam foundations are there in terms of flexibility, we know that the frequencies will be increases, and at that time we need to put a clear frequency check and the same time insertion losses with these models, and we need to add those features along with YP, YI and YM in computation of these insertion losses. So that's what you see here, the transformation of these two, we can say sound when it is propagating at these exciting frequencies. In the next model, now we can say that we have a military ship which is being just moving at a certain speed, and the vibration machines of such vessels must be isolated. And for that, you see here, we need to take a necessary action. We can say some kind of double isolation, or even you see in the railway feature also, we know that when the excitations are so high and we just want to comfort the situation inside the cabin, there are, you see, the double isolations are there. So this is what you see in some kind of, even not only in the military ships, but also see in the various vehicles where such kind of requirements are required, or essentially the steps would be required to eliminate such kind of vibration. We are taking now such kind of example that we have a machine, and you see here some added mass is there. So machine mass is M1, the added mass is M2, and now you see the isolator in between the machine and added mass is just the composite spring, say at the rate of K1, and those in between the added masses and the foundation is also having the composite spring at the rate of K2. So we have the 4 parameters here, one M1 and M2. M1 is the main machine mass, M2 is the mass which is simply added mass. The spring K1 is in between the machine and mass, and K2 in between the mass, the added mass and the foundation. Now if you are assuming that this is whatever the mounting points are there, they are not providing some kind of flexibility, so they are the rigid one. Now we just want to prove in this case that the insertion losses for transmission, the force transmission is DL equals to 20 log Ym plus Yi divided by Ym. No, though there is no Yp here, where the stiffness, we can say the equivalent stiffness, the spring rate, you see, K1 is equals to the Ki, rather we can say the Ki integrated one for this Yi equals to K1 divided by 1 plus K1 by K2 plus K1 by K2 into M2 by M1 minus omega square K2 by M2. So this part which we need to show. Also we need to show the insertion loss at the higher frequency when it has been increases at the rate of 80 decibel per decade. So in the solution now, first of all we know that the two springs are being acted in between machine to foundation, and these springs are the elastic springs. So, we can straightway apply the forces in between this. So, when we are saying that in between, you see the machine to the added mass, since machine mass is m1, so m1 into d2x1 by dt square inertia force equals to the excitation force minus the F1 force. And the F2 force which is being applied to the foundation from the equation, from the like we can say the entire excitation of the machine, then we can straightway put the F2 in the lower one. So, we have the two masses and the two spring in between, you see like the entire feature. M1 is having, you see, the x1 displacement, M2 the added mass having the displacement of x2. So, F1 which is the force with the mass m1 is nothing but equals to the restoring part k1 into x1 minus x2, the difference of these two displacement, the effective formulation of restoring forces. And when we are talking about the mass m2, the added mass, m2 into d2 x2 divided by dt square equals to F1 minus F2. So, either when we are making force balance for mass m1 which is nothing but in between the restoring force and excitation force, and when we are talking about the mass balance in between, means that for this added mass in between, you see like the k1 and k2. So, we have F1 and F2, the resultant of these two restoring forces, where F2 is k2 x2, F1 is k1 x1 minus x2. So, these are the basic force balance equations for such systems, and when we are trying to eliminate the x2 and F1, then we have minus m1 omega square x1 equals to the F, whatever the storage feature, minus k1 into x1 minus F2 by k2, and when we are just making balance of these things, we have minus m2 omega square F2 by k2 equals to k1 into x1 minus F2, which is the excitation force at the foundation, divided by k2 minus F2. This is what it is. You see here we are trying to modify the equation based on the elimination of x2 and F1. Similarly, we can go with the elimination of x1 and F2. So, like when we are trying these things, so F2 which is nothing but the force at the foundation from the excitation of the machine is nothing but equals to the storage F storage divided by 1 minus omega square m1 divided by k1 plus m divided by k2, whatever you see the masses which are being coming out to do that, plus m2 divided by k2 plus omega square of this part. So, you see here like when we are trying to see these things, we know that the exciting frequencies in between, you see like k1 and k2 part spring can be straightway get, and when we are trying to see the force on the foundation, when they are just coming equal to the excitation force, the sound propagation is used, and if you want to find the insertion loss dl, it is nothing but equals to the 20 log f excitation divided by F2. So, how much excitation force is there and how much force is being transmitted to the foundation? If there is no, we can say, isolation system, immediately it will transfer out and we can get the 20 log 1 minus omega square. No k by m is there in that case. So, now you see, but if we want to put the entire system, then we have 20 log 1 minus omega square m1 k1 m1 divided by k1 plus m2 into k2, m1 into k2 plus m2 by k2 plus whatever the omega 4, the down feature omega 4 m1 divided by k1 into m2 divided by k2. So, this is what you see, a clear transmission of the forces from excitation to foundation through these springs up to the ground part. And when we are trying to put these values, we know that it is nothing but equals to 20 log. Again, you see when you are trying to modify these things, 20 log 1 minus omega square m2 plus you see 1 minus 1 divided by k1 plus 1 divided by k2 plus m2 by m1 into k2 we can say, and minus m2 k1 k2 omega square. So, when we are trying to compare those things, we know that it is a clear transformation of the entire forces from the excitation to the sink, and when we are comparing these things, we know that the insertion losses in such cases is 20 log 1 minus omega square by k by m. So, this is what you see in these connections, that how the insertion losses can be computed. And when this excitation frequency is just like gets large, then certainly we know that the highest power of my exciting frequency omega becomes certainly dominant at the higher harmonics node. So, in that case the insertion losses will be almost equal to all other feature like omega square m1, and then you see like this m1 m2 by m1 k2, they are all you see though they are present, but the dominancy will be coming from the omega 4. So, when you are computing this, the insertion losses, this is almost nearly equal to 20 log m1 m2 by k1 k2 omega to the power 4, or else we can say that it is nothing but equals to 80 log exciting frequency plus 20 log m1 m2 by k1 k2. So, like from this we can immediately compute that you see like what is the insertion losses when we are featuring out at the higher harmonics node. In another numerical you see here, now our thing is a machine is to be mounted on the thin like the steel plate where the mobility is Yu, and if we are saying that the machine is vibrating as a point mass m which is perpendicular to the plane of the plate, certainly you see when it is just going as, after some time you see it is unacceptable to find out you see the vibration level and the noise level. Now, we would like to see that how we can like improve the vibration isolation of the machine. So, you can see that there are three like the figures are there. So, that is what you see the machine which is mounted on the steel plate first, which has the 50 kilogram of mass. The first arrangement in this is given as the spring of say 10 kilonewton per meter stiffness is being added in between the machine to the foundation. The second feature says that why do not we add with this like added mass there itself. So, we have a 2 kilogram of added mass to the ground to suppress the another amount of the energy towards the excitation. So, when you have these three arrangements, so first question is that mass of machine is say 50 kilogram and all these like the plate is 3 millimeter thick and the plate is regarded as an infinite in the extent, what is the insertion loss could be obtained at the 100 hertz of the exciting frequency with the spring rate is 10 kilonewton per meter. So, this is what my exciting frequency, and I would like to find out the insertion loss. In the second feature, with the spring rate say 10 kilonewton per meter is not perfect isolator as compared to the as in the first case. So, like to make further improvement towards the insertion losses of the plate, just like additional 2 kilogram of mass is to be provided at the lower, as we shown in the previous diagram. So, now you see the insertion losses can be calculated by replacing the mobility Yu by the total mobility as Y total equals to like 1 divided by I omega m, that is Ym plus Yu to the power minus 1. So, that's what you see we want to show that. So, now you see here the first case was this, the second case was the mobility replacement in the total, and the third case is that the insertion loss is at the 100 hertz frequency if the added mass is 2 kilograms. So, how much you see the insertion losses are there at that exciting frequency. So, the first case the mobility is nothing but the inverse case of the impedance as we know that. So, we can calculate the impedance Ym, the impedance equals to 1 by I omega m. So, now we have 1 divided by iota, the omega is 2 pi into 100 is the excitation frequency, and m is given as 50 kilogram of the mass. So, we have you see the impedance due to the mass figure, it is minus 10 minus iota 0.032 into 10 raised to power 3 meter per Newton second, just the reverse of the mobility. And yi, the impedance due to this stiffness or the restoring forces is I omega by k, as we discussed already. So it is nothing but equals to iota 2 pi, the f is given as 100 hertz divided by 10 into 10 raised to power 3. That's what it is. You see the 10 kilonewton per meter, the stiffness variation. So we have now the yi equals to 62.8 into 10 raised to power minus 3 meter per Newton second. So we have ym, we have yi, whatever you see the impedances are there in that. So we can find out, you see, the yu, that is nothing but equals to 1 over 8 square root of 8 the d rho h, or we can say it is nothing but equals to 8 e h cube divided by 12 into 1 minus mu square rho h. When we are keeping those things, we have yu is nothing but equals to 1.16 into 10 raised to power minus 3 meter over Newton second. So you see, when we are calculating this, we can straightway go to now our insertion losses, that is nothing but equals to 20 log ym plus yi plus yu divided by ym plus yu. And when we are keeping these values there, like you see the ym is given as minus iota 0.032 into 10 raised to power minus 3, yi is nothing but equals to iota 62.8 into 10 raised to power minus 3, and yu is 1.16 into 10 raised to power minus 3 divided by, you see, ym plus yu, then the insertion losses are almost nearly equals to 35 decibels. So this is what you see, the first case in which you see we have a direct insertion loss at the 100 hertz exciting frequency. The second case is that when you have the the insertion losses which you would like to calculate, absolutely when we are just making an additional mass m at the mounting position, and we would like to calculate the mobility at the mounting point, the total mobility in terms of the yu inverse and I omega m because of the additional mass m. So we can say that in this figure, since you see here you have the F, the exciting forces which is being there with the masses there, and there is an additional mass which is being there at the lower end. So with the force balance you can say that you have F and F1 which is being like the lowered feature, and that this is, you see, the velocity which is being there in between the eccentricity of that part. So we can say that in total we have a velocity V2 of this mass, V1 with this foundation, and you see the F1 which is being acted on that, on the upper part, on the the top side of this mass at equal and opposite direction to whatever the foundation part is, because this mass is being added here. So with this now we can calculate the V equals to y total F, because the total, you see, we would like to find out this one, where the V1 is nothing but equals to the mobility at the u, at the whatever the u velocity. So V1 equals to yu, F minus F1, whatever the differences are there in between these two forces, and where F1 which is basically there due to the mass, added mass there, is I omega m, this is the added mass m into V2. And since you see the mass and the plates are just fastened together, we are assuming that there is no voltage, there is no velocity differences there. We are not assuming any loss of this one. So V1 equals to V2 equals to V, and when we are keeping those things and we would like to find out the V, that is nothing but equals to yu, F, the total force, minus I omega m into V. This is what my F1 was there earlier. So now you see we can straightway calculate yu equals to V by F, where it is y total we would like to calculate. So it is yu V divided by I 1 plus I omega m yu, or else you see here when we are just dividing these things, it is equals to 1 divided by I omega m plus y to the power minus 1. So you see here the insertion losses for that can be straightway exchanged when you see, when you are just exchanging yu with the added mass, and the new mobility for the foundation, if the 2 kilogram is being added exactly at the 100 hertz of frequency, then the y total is 1 divided by 1 of 1.16 into 10 raised to power minus 3 plus I omega, that is was omega is 2 pi f, means 2 pi 100 into 2, the added mass is there 2 pi omega m. So, it is almost nearly equals to 1 divided by 862.1 plus iota 1257. So, this is what you see the total mobility, or total we can say the kind of impedances can be calculated with that, and when we are just putting those things, the insertion losses in this is nothing but equals to 20 log yu plus ym divided by the yu. So, when you are putting all these things, it is almost nearly equals to the 40 dB, or else we can say that it is 5 dB increment is there at the every stage of this one in the insertion losses at the 100 hertz of this one. So, this is you see the insertion loss calculation for any kind of exciting sources when they are being converted towards you see the mobility and the impedances features. In the last example, now we are considering you see a different kind of you see the matrices. You have the mass matrix, you have the damping matrix, and you have the stiffness matrices together. And now you see we would like to calculate for multi degree of freedom system, say you see because it is like the matrices are given, would like to calculate that what exactly the damping ratios for that, and what the critical damping features are there. So, critical damping is nothing but equals to d critical equals to 2 k to the power half. So, we can say that this matrix is nothing but equals to, we can simply a square root of this stiffness matrices. So, we have 4.42 minus 0.63 minus 0.63 and 1.8. So, this is what my critical damping matrix, and then when we are putting this matrix to the main equation of k, which is nothing but equals to m inverse half k m inverse half, or even m inverse minus m minus 1 k m 1. So, it is what you see the balanced equation which we discussed you see in the last chapter of that. So, the damping matrix ratio, whatever you see the damping ratios are there in the matrix form, it is nothing but equals to 0.35 minus 0.22 minus 0.22, that is what the symmetricity, and 0.466. And it is clear that the matrix I minus Z is positive definite, and you see here we can straightway calculate that this is what the case of the underdamped system, where the zeta, the damping ratio, which is nothing but equals to even the the damping critical and available, or the frequency excitation, the damped and undamped is always underdamped system. So, that is I minus Z, we can calculate 0.35, 0.22, 0.22 and 0.53 can be straightway calculated. So, with this you see here we can say that we can simply find out the determinant of this, and it is you see the less than 0.1432. It is a positive definite. So, we can say that this is what the underdamped system, and we can calculate you see the eigenvalues for this Z matrix, which is nothing but equals to 0.7906, and you see the lambda is 0.3126. So, you see here in this case whatever you see the lambda 1 and lambda 2 are absolutely you see greater than 0, but you see they are going towards you see less than 1, because they are all you see 0.79 and 0.31. We can say that this is absolutely a underdamped system in which you have in phase and out phase of both the masses, as the matrix are just showing the two the 4 elements in the 2 rows. So, certainly you see we have the 2 degrees of system, and both the masses are in and out phase, and in between we can say the mode shapes are at 0 and 1. So, we can say that in the underdamped system this can be easily calculated. So, you see the lambda 1 and lambda 2, because you see we know that we just want to find out this the total amplitude. So, it is nothing but equals to 0.337 plus this 0.8326 j, or else we can say that the another feature is minus 166 plus this one. So, in this case we can say that each mode underdamped system you see predicted by both the damping ratio and modal damping ratio Z1. So, we can say that in such cases when the underdamped systems are there, we have exponential decay in the oscillatory feature with the sinusoidal features are there. So, you have both coefficients lambda 1 comma 2 and lambda 3 comma 2 with the this damping ratio matrix in this form, where you have 0.33 plus iota times of plus minus iota times and 166 plus iota times of these things. So, the first lambda 1 comma 2 is showing in phase, and lambda 3 comma 4 is showing out phase as minus 166 plus minus of this. So these are the numerical problems which are closely related to the insertion losses when the the exciting frequency of vibration and the sound propagations are there, and how much when we are keeping isolators in various ways, then how we can interrupt the path or interrupt even at the source itself when the insertion losses are being there in relation to mobility or the impedance of that. And if the if the large difference is there, certainly we can say that the isolator has to be checked according to the insertion losses. The last numerical was there related to the multi-degree of freedom system, where we can calculate the damping ratio for underdamped or the critical damped feature. So these numerical problems are just showing, along with whatever the theory which we discussed, the internal mechanism or the physical sense of those problems along with this. Now in the next lecture, we would like to discuss about the another module where you see here, we are going to discuss about the requirement of the vibration isolation features in this, when the materials or the damping or any other features are there related to the vibration control part. Thank you.